Viewers like you make this program possible. Support your local PBS station.
Why do bombs go boom?
You have created fire! I can feel that puppy.
How much gold is in 400 tons of dirt?
There's about $1.5 million there.
Oh, man! What's that gorilla doing there?
And how come rare earths, the metals that make our gadgets go, aren't that rare at all?
Watch out with the hammer. What do you...
Oh, yeah. Cerium, lanthanum, praseodymium.
We live in a world of incredible material variety. Yet everything we know, the stars, the planets, and life itself, comes from about 90 basic building blocks.
You have a periodic table.
All right here, on this remarkable chart, the periodic table of the elements. It's a story that begins with the Big Bang and eventually leads to us. And we're made almost entirely of just a handful of ingredients, including one that burns with secret fire inside us all. Join me as I explore the basic building blocks of the universe.
As hard as you can.
From some of the most common,
You can do it.
like oxygen,
How do you feel at this stage?
to the least, man-made elements that last only fractions of a second. Strange metals with repellent powers.
And you're saying that this will repel the sharks. Oh, my gosh! Ugh!
Poisonous gases.
Isn't chlorine deadly?
Absolutely.
In stuff we eat every day. And now, we can even see what they're made of.
The dots are actual atoms?
If you're like me, you care about the elements and how they go together.
Oh, the humanity!
Because more than ever,
Incoming neutrons!
matter matters.
Copper is king.
Commodities, copper at 80 cents a pound.
Can we crack the code to build the world of the future? Join me on my hunt for the elements. Right now on Nova.
Major funding for NOVA is provided by the following.
Far from prying eyes, the ground erupts. Heavy equipment moving millions of tons of earth in search of something. A secret deep underground. I'm David Pogue. I've managed to talk my way into this hidden lair.
Probably almost a mile from when we first came in.
Boy, I hope I can talk my way out.
This area here has been backfilled.
They tell me that so much money flows out of this place, it's like a gold mine. Wait a minute. It is a gold mine. But where's the gold? It turns out that nature has concealed thousands of pounds of the stuff under billions of cubic feet of earth. By digging, these guys are hoping to strike it rich. But that's not why I'm here. I'm on a quest to understand the basic building blocks of everyday matter. They're called the elements. These symbols represent the atoms that make up every single thing in our universe. 118 unique substances arranged on an amazing chart that reveals their hidden secrets to anyone who knows how to read it. It's a journey that dives deep into the metals of civilization, marvels at the mysteries of the extremely reactive, reveals hidden powers, and harnesses secrets of life, from hydrogen to uranium and beyond. I'm starting with one of humanity's first elemental loves, gold, symbol AU. Like all elements, gold is an atom that gets its identity from tiny particles, positively charged protons in the nucleus, balanced by negatively charged electrons all around, plus neutrons which have no charge at all. Gold has been sought since ancient times, yet all the gold ever mined would fit into a single cube about 60 feet on a side. Gold is unique among the metals. It doesn't rust or tarnish. It's virtually indestructible, yet also soft and malleable. It was a sacred material to ancient people. and it's never lost its luster. The problem is, it's exceedingly rare stuff in the Earth's crust, and it's getting harder to find all the time. Here at the Cortez Mine in Nevada, high-tech prospectors are moving mountains, closing in from above and below. This rock face is about a quarter mile below the surface. And according to John Tolley, it's loaded with gold. Somewhere.
And what would it look like? Like yellow metallic streaks in the walls?
No, it's really hard to tell from the rock because it's microscopic. You can't see the gold.
The gold is microscopic?
Yes, you can't see it with the naked eye.
So we're way past the days of finding big gold nuggets sticking out of the wall, going, "Hey, Bob, I got one here." We're past that now, huh?
That's correct.
Which raises a question. If the gold is invisible to the naked eye, how do they even know if they're digging in the right place? That's where Gail Fitzwater and the assay team come in. Every day, she receives hundreds of samples of earth taken from the mine. Her job is to figure out how much gold is in them there rocks. To get at the color, it has to be crushed,
You want ice cream with this?
shuffled like a deck of cards,
I think I've seen one of these machines at Starbucks.
then pulverized to the consistency of baby powder.
I don't see any more rocks in here. But the bad news is I don't see any gold in here either.
The good news is that we haven't finished. There may be still gold hiding in the mix. The sample, mixed with a lead oxide powder, goes into a furnace heated to 2,000 degrees. It's a 500-year-old process called a fire assay. Using extreme heat, gold atoms are gradually coaxed away from the powdered rock.
So after all that pulverizing and crushing and weighing and firing, what we're left with is this, these little teacups?
What you're going to be able to see in here is a gold bead that was recovered from that sample that you crushed.
No.
Okay,
This is
come
like
on.
the Emperor's new teacup. There's nothing in here. Wait, except that little tiny piece of dust.
That's a piece of gold. That actually weighs about 1/2 milligram.
So all that work gave you only 1/2 milligram of gold?
It equals out to about 1 ounce per ton.
An ounce of gold for every ton of rock?
That's right. And
That's a terrible business. You'll never make any money.
when you went in the mine and you were able to see the trucks that we had,
Yeah.
those are 400-ton haul packs. If you had 400 tons of material at 1 ounce per ton,
400 tons and 1 ounce of gold for each ton. At that rate, that's 25 pounds of gold for every truck.
and at $1,800 an ounce,
$1,800 times 60. $720,000 a truck. This is a fantastic business. How do I get in on this?
Turns out that an ounce per ton is pretty much optimal for the underground mine. The surface mine produces less, about 1/2 ounce per ton. To see what it takes to get something bigger than that tiny bead, I visit the processing plant where the ore ends up.
Just another day in the gold refinery.
Here, too, extraction begins with crushing in these huge tumblers. And that sets the stage for the trickiest step, coaxing the microscopic gold out of the rocky ore. About 3/4 of the elements are metals, and gold is one of the most standoffish. How an atom reacts chemically depends on how willing it is to share electrons with others. And gold is not very social. Like Greta Garbo, it wants to be alone. So do other so-called noble metals. Silver, platinum, palladium, osmium, and iridium, all located in the same quiet neighborhood of the periodic table. Using cyanide to react with the gold allows them to gradually reduce 40,000-gallon tanks of pulverized sludge to this, 3 trays full of mud?
But there's not gold in here, is there?
There's a little bit of carbon that's mixed in with this that's changed the color on it. But I assure you that when we melt it and pour it down, Dave, we're going to have gold.
All right, and how much gold, like how many gold bars will this array make?
This should produce about 1.5 bars.
All right, and all derived from one 40,000 gallon batch of solution.
Right.
So 40,000 gallons got distilled down to this, and that will get distilled down to 1.5 bars?
Right.
Wow.
Exactly.
The golden mud goes into a 2,000-degree induction furnace, along with a white powder called flux, chemicals that prevent the molten gold from reacting with or sticking to anything. This is the first time an outsider has been allowed to pour gold. Just call me King Midas.
I'm not sure they entirely know what they're doing, but they are going to let me pour the gold into a gold bar mold. If it goes over 70 pounds, it's a reject. They'll have to throw it away or just let me take it home in my luggage. So, you know, I'll do my best not to spill.
There's a lot of money at stake here.
Here it comes. Hot gold. Get your hot gold, yeah? Right there. It's a gold bar, ladies and gentlemen. It's been my pleasure. See you next week. Perfect job.
Final steps: cool and clean the bars. Stamp them with their unique serial numbers and their weights.
So this is it, the proverbial gold bars. And you know what? They're still warm.
They're still warm. Hot off the press.
Can I pick one of these up? It's not may I, it's can I. Oh, man! This thing, so this is what, 70 pounds?
It's about 60 pounds.
60 pounds?
Yeah.
Oh, it's nothing. And about how much value here?
There's about $1.5 million there, Dave.
Oh, man. Mike, what's that gorilla doing there?
They're deceptively heavy. Only a few natural elements have greater density than gold: rhenium, platinum, iridium, and osmium. Mike tells me that each bar represents about 1 million pounds of rock that had to be moved and processed. 8 bars, $12 million, sitting on this unassuming little table. What a transformation. Of all the elements that touch our lives, nothing drives humankind to acts of love or destruction like gold. It is perhaps the most emotional of the elements. But 2 rows above gold is another metal of antiquity that looms large in our lives. Copper. Symbol Cu. Atomic number 29. 29 protons, 29 electrons. The ancients first learned how to heat rocks to extract copper at least 7,000 years ago. And today, it's one of the most widely bought and sold metals in the world. The New York Mercantile Exchange is a vital hub in the global metals market, which is pretty good news for me. At least I thought so.
Sorry, sir, you can't come in with us.
I thought this is a copper exchange. I'm here to exchange some copper.
I'm sorry, that's not allowed on the floor. You can't come in with us.
Seriously?
The only business that they're willing to do here is to buy or sell copper futures. Like, who would fall for that?
Oh, this is an old business. This goes back to the 1800s, the late 1800s, where farmers were looking actually for money to plant their next year's crops. So what the farmers would do is they would say, for example, David, you loan me some money, okay, and then in the future, I will sell you that crop that I planted for this amount of dollars.
18 style at 5.
So what I'm doing is I'm selling you the right to buy or sell my future crops.
So this crazy high-tech thing began as a glorified farmer's market.
In fact, this exchange in New York started as a butter and cheese exchange on Harrison Street.
Is it safe to say there's no cheese pit here somewhere? Gruyere, cheddar.
David, you have to go to Chicago for that.
They still do that?
They still trade agricultural products.
I would think that there would be trading markets like this for gold and silver and platinum and things that are valuable. But copper? Come on, it's like pennies.
Copper is king, okay? Copper is used for everything. It's a really vital metal. We use it for infrastructure. We use it for electronic goods. I can hardly think of anything that doesn't have either a tiny bit of copper or lots of copper. I love copper. I do.
I'm getting that.
Harriet tells me that the copper market is huge. Traders in New York, London, and Shanghai buy and sell more than 20 million tons a year. Copper is in wire, electronics, and computer chips, plumbing, and other building materials. It's so important that the rise and fall of copper prices provide a snapshot of the health of the entire world economy. When times are bad, copper prices tumble, and when times are good, they soar. Some say it should be called Dr. Copper because it's the only metal with a PhD in economics. Copper has been prized for millennia for its unique properties. It conducts electricity better than any metal except silver. It's malleable and has a moderate melting temperature. It even scares away bacteria.
Out of control, Joe. I'm screaming 6 times and no.
These guys can trade their copper futures. I've got to unload my copper today.
Commodities! Get your commodities! Got copper at 80 cents a pound. Anybody? Anybody?
Copper alone is impressive stuff, but when ancient metallurgists combined it with another element, they invented a much tougher material that went on to conquer the world. That secret ingredient? Tin. Symbol SN. Atomic number 50. 50 protons and 50 electrons. Tin, added in small amounts to copper, makes bronze, the first man-made metal alloy. Bronze helped to spur global trade, and once forged into tools and weapons, it played a defining role in the empires of antiquity. Bronze named an entire age of human civilization. And even today, it's still hanging around. This is the Verdun Company, a 170-year-old family-run business in Cincinnati, Ohio. I'm here because they're about to cast several bells. Even with all the other modern materials available, they still choose bronze. I want to know why. Hasn't something better come along after all these years? Ralph Young offers to make the case for bronze.
This is our pattern that we're going to use to actually make the form in the sand.
So this looks like a finished bell. This isn't
Yes,
a bell?
it does. This is just the pattern, yes. It's made out of aluminum, so it's real easy to handle.
Well, what's wrong with it? Aluminum's good. Aluminum doesn't rust. Aluminum's light.
You're right.
Why don't you make the bells out of this?
Well, the sound. It doesn't have that lasting ring, and it's just...
You don't like how that sounds?
It's not really. It sounds kind of tinny also.
Thanks a lot, buddy.
Yeah, well, you know.
I practiced.
We'll show you what a real bell sounds like.
The quality of the sound depends on the atomic structure of the material. In pure metals, the atoms are arranged in orderly rows and columns. Each atom gives up some of its electrons to create a kind of sea of these randomly moving charged particles. It's these free-flowing electrons that make metals conductive. When placed in a circuit, the negatively charged particles line up and flow as an electric current. The sea of electrons also creates flexible metallic bonds among the atoms. In copper, they can slide past each other easily, which makes it relatively soft and easy to dent. Not right for a bell. That's why Verdun uses stiffer stuff.
So we'll put this down into here.
Ralph places the form into a circular steel sleeve, then fills the space around it with a mixture of sand and epoxy to withstand the searing heat of the hot metal. When this company started, they used a mixture of horsehair, manure, and just about anything else that would hold a shape without burning. But the goal was the same: to create a hollow shape that follows the inner and outer perimeter of the bell. Once he removes the aluminum and joins the two halves, a bell-shaped space remains on the inside, ready to accept the molten bronze.
And what we have here, David, is the bronze ingots that we use to put in the furnace. As you can see, they've got a little bit of heft to them.
Yeah.
They average about 20 pounds. That's a mixture, actually, of 80% copper and 20% tin. And what we have here is the tin in a raw form. This is how it comes out of the ground. This is from Malaysia.
Okay.
And we have a chunk of copper, the way it comes out of the ground, and that's from South Africa.
So that's the recipe for bronze. So
Exactly.
Copper plus tin equals bronze.
Equals bronze, yeah.
Why couldn't you use one of those metals by themselves? Why don't you make bells out of just copper?
If it was all copper, it would first of all be too soft, and we wouldn't get that sound that we want from a bell. Tin with copper gives us that hardness.
Adding tin to copper during melting changes the properties of the metal. The larger tin atoms restrict the movement of the copper atoms, making the material harder. A blow causes the atoms to vibrate, but the tin prevents them from moving too far out of position. Tin is good for a bell, but only in the right proportion. This is what can happen if the amount of tin isn't right. No one is certain why the Liberty Bell cracked, but a chemical analysis indicated that there was too much tin and perhaps other impurities in the bronze. The crack could have been caused by the way the atoms were arranged within the metal. Too much tin and the copper atoms can't move at all. One good whack and... When the bronze has reached the proper temperature, 2200 degrees Fahrenheit, it's time to pour.
Is there any danger involved in this process?
Well, if you consider getting burned a danger, yes, there is.
During the pour, speed is of the essence. If the metal is allowed to cool, flaws could develop, ruining the bell. Even though the foundry has the technology to precisely control the temperature, and Ralph and his team have decades of experience, bronze remains unpredictable. Out of every 100 bells they pour, 20 or 30 will fail.
That was quite a process. I appreciate your letting me help out like that.
I think we got 3 successful bells out of this, but anything can go wrong. So you just don't know until after you open up the molds and see what you got.
The bells have to cool for 24 hours. So it's the next day before we can find out if they'll be making music or ending up as scrap.
So what am I going to see inside? A gleaming, chrome, silver, magnificent church bell ready for hanging?
Actually, no. You're going to see, I like to refer to them as a newborn baby. They come out kind of ugly and not so pretty, but they clean up really well.
Bum, 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 bum. Wow, I can feel waves of heat coming off of this.
Yes, it's still quite warm.
Is it touchable?
Yes, it's touchable.
How? Speak for yourself, dude.
And what happens to a carefully crafted sand mold? It's history.
Is this an actual bell that you can actually sell to somebody?
Oh, yes, yes. This will be on the market very soon.
So I really do need to not chip it.
That would be good.
So, what about all this black, sooty stuff?
So that's going to have to be cleaned off of there.
You got some kind of big hydraulic?
Actually, no. I got this. Well, that was a big waste of time. You missed a big spot over here. I guess that's okay for a rookie.
Well, thank you so much, Ralph.
And now for the moment of truth. Will this bell be good enough to sing?
What time is it? Time to celebrate the millennia-old tradition of bronze.
Our bell resonates with a beautiful tone, and it takes many seconds for the note to die out, thanks to the interplay between copper and tin. Even the best bell makers can't know whether their bronze will be too stiff or too soft until they pour a bell and strike it. I wonder, though, if there's a more scientific way to evaluate the metal. To find out, I'm taking a piece of it to David Muller at Cornell University. He's offered to show me how the atoms in our bronze stack up, literally.
Oh, I see. I brought you a couple of hunks of bronze, one of which was knocked off of the bell when it was done, and one of which is unpoured. And I wouldn't mind taking a look at these under your magic microscope.
Okay, now, this is actually a lot of material. I need an area about the size of a farm, and you've given me the whole of the United States. So we're going to cut it down a little bit. Now, watch out, it's hot.
It's what? Ow!
First, a polishing wheel gives the bronze a mirror-like finish. Then the sample is inserted into a powerful electron microscope. David tells me that when we reach full magnification, we will have images of the actual atoms in the bronze. Something few people have ever seen. Frankly, it seems a little far-fetched.
So what's in there right now? What are we looking at?
So we have a piece of the bronze that we cut earlier, very similar to this one.
Now, I have to say, this microscope is not especially impressive. I mean, I'm seeing the entire circle like I'm just wearing a pair of reading glasses or something.
So this is like having a map of the United States, and eventually we want to zoom in, and we want to pick out one car parked somewhere in the U.S.
We'll have to zoom in 100 million times to see an atom. To understand the scale, imagine if I were floating in space 2,000 miles above the Earth, looking down at the United States. Zooming in 100 million times would allow me to pick out not just a car, but a bug crawling in the grass next to it.
So we can zoom in from here?
Absolutely.
How do you do that?
So there's the zoom button.
The big knob labeled magnification?
Absolutely. So crank up the mag and let's see what happens as you zoom in.
Wait, I see a little tiny cartoon sign that says, "Welcome to Whoville."
To see atoms, we need to find an interesting region to sample.
Now it's starting to look like an alien surface.
Right. Now what we're actually starting to see is the microstructure of the grains in that bronze. And the brighter colors are things that contain more tin. And the things with less tin are the things that are slightly darker.
Oh my gosh, that is so cool.
The microscopic structure of metals is not uniform. Small features called grains become visible. Boundaries between grains are actually defects in the orderly arrangement of the atoms.
So you can't see atoms with this microscope?
We can get almost all the way there, but not quite.
Okay.
And to look at atoms, we're going to need a bigger machine.
Do you have one?
We certainly do.
This huge thing? This giant room-sized thing in a shipping container? And why is it draped in shipping crate material?
Those are acoustic blankets. They are meant to absorb and reflect sound because the microscope itself is so sensitive that if you were to talk, just the pressure wave from your voice is going to give enough mechanical vibration to shake this thing around. We only have to shake things by an atom for the image to vanish.
Oh, so our little piece of bronze that we've dug out of the first machine is now the little black disc there?
Well, that's the 3mm support disc. The actual bronze chip itself is about 1/100th the thickness of a human hair. It's too small for us to see, so we have to mount it on a carrier grid so we can handle it.
Oh, so you've essentially put it on a little plate?
That's right.
Are you telling me that I can see individual atoms of my piece of bell?
That's correct.
Scientists have understood since the early 20th century that metals are crystals. That is, they have an orderly arrangement of atoms. By bombarding samples with X-rays, they were able to create shadowy images of that crystal structure. But the idea that we might one day see actual atoms was beyond imagination. If David's microscope is powerful enough, we should see regular rows of copper atoms with tin atoms packed in between. Or so the theory predicts.
The dots are atoms?
That's right. Each individual dot is an atom.
We are seeing actual atoms of my little bell piece?
The bright ones, those are the tin atoms, and the slightly darker ones, those are the copper atoms.
And isn't it kind of like a mind blower that we're actually looking at actual atoms? I mean, isn't this a historic technological achievement?
Every time people see that for the first time, they get really excited.
To actually see atoms. Amazing.
Well, what can we learn about this? Like for one thing, I noticed they're really, really grid-like. They're like a little aerial photo of a planned community.
That's actually the stacking of the atoms in the material. The pattern that it orders into, that is the crystal structure directly.
David tells me we got very lucky. The atoms in our bronze are unusually well ordered. Our bell makers must be true masters of their craft.
Well, thanks for my tour into the unseen, into what used to be the purely theoretical. I can't believe I can now put on my resume that I've seen atoms. Thanks for the tour.
It was a pleasure.
This amazing ability to see atoms has opened up new worlds for scientists. Muller's lab has successfully captured many other images of atoms in gold and computer chips, oxygen, powerful magnets, and even glass. But even so, they've barely scratched the surface because they can discern only the outermost boundaries around atoms. The interior is 10,000 times smaller. If the outer boundary of a hydrogen atom, where the electron is found, were enlarged to be 2 miles wide, about the size of a city, the single proton in its nucleus would be the size of a golf ball. It's here we find elements at their most elemental, because every nucleus contains protons, and it's the number of protons that determines what kind of element the atom is. 1 proton is hydrogen. 2 protons, helium. 3 protons, lithium. 4 protons, beryllium, all the way up to element 118, with 118 protons. The number of protons is called the atomic number, and it's the fundamental organizing principle of every table of the elements, including this one.
Wow, this is cool. You have a periodic table.
Well, it's called a periodic table. Why do people keep putting them on the wall?
Every high school student has seen the elements chart, but author Theo Gray's version is unique. Handmade, with each element's identity card meticulously carved into the wood.
But I have to say I've never completely gotten it, right? They're filled with stats and figures that don't make any sense to an ordinary person.
Theo gives me a refresher.
You've got the name of the element. You've got the atomic symbol.
Ca for calcium.
You've got the atomic number, which is the number of protons in the nucleus of each atom of that element. It's probably the most important thing on this tile.
So where's gold?
Gold's right there, number 79.
Okay, so here's a classic example. They would do much better with marketing this table if the name and the symbol matched. Gold doesn't even have AU in it.
The symbol is based on the Latin name, aurum. And if you think about it, the name of each element is the least important piece of information you could possibly have. What matters about elements is that they are real physical substances with properties and things you can do with them.
Theo makes the point by putting me in touch with the real deal.
Oh, I see what you've done.
To make the entire table less abstract, he invites me to lay out the rest of his collection of pure elements.
Well, this is really pretty amazing. This is a visual representation of every single element that makes up this entire planet and everything on it.
Then, Theo reminds me of something I'd forgotten. As we can clearly see, more than 70% of the elements on the table are metals, shiny, malleable materials that conduct electricity.
There's sort of a diagonal line here. Everything from here on over, including the bottom part, is all metals. Everything from here on over is non-metals. And down the middle are these kind of halfway in-between things, which include, for example, semiconductors, like silicon.
Right? I have to say, many of these elements look the way you would think. Gold looks like gold, silver looks like silver, but not all of them. The one I was looking at in particular is calcium. Most people probably think of calcium as white and chalky. It's bone, it's chalk, it's milk. But this is a silver shiny metal.
This is when Teo's collection starts to get really interesting, when he pairs the pure elements with their more familiar forms, like pure calcium metal combined with other elements to make bone, bismuth in stomach medicine, bromine in soda, and even this element hiding out in collectible Fiesta ware. This bowl from the 1930s gets its orange color from uranium, and it's actually dangerously radioactive. Teo's table and his remarkable collection make a powerful point. From about 90 elements found on Earth, nature and man have derived millions of different substances that make our world. But to me, there's something even more amazing. The table organizes the elements by atomic number. That is, the number of protons in each atom. Yet the table's creator, a 19th century Russian chemistry professor named Dmitry Mendeleev, knew nothing about protons or atomic numbers. Even the atom itself hadn't been discovered. To understand how he cracked the code of the table, I've come to St. Petersburg, Russia, to the State University, and to Mendeleev's apartment and office. In the late 1860s, at this very desk, Mendeleev set out to discover the underlying order to the elements. In one often repeated story, Mendeleev is said to have created 63 cards, one for each of the elements known at the time. He distinguished them not by atomic number, but by atomic weight.
So he didn't know about atoms, but isn't this the atomic weight? How does he know the weight if he doesn't know about atoms?
Разумеется, взвешивать атом в граммах.
It's not in grams or pounds or kilograms. In the 19th century, they did it like this. They compared the weights of different elements to the lightest, hydrogen. So when they say oxygen is 16, that means 16 times the weight of hydrogen.
19th century scientists relied on relative weight to order the elements. Imagine if you have two containers, one full of red marbles, one full of blue marbles. If both contain the same number of marbles, but the blue container weighs twice as much, you can infer that the blue marbles weigh twice as much as the red marbles, even if you can't see the marbles at all. Early chemists devised clever ways of calculating the weights of elements, even gases, relative to the lightest one, hydrogen.
So the chemists knew that different elements have different weights, but why not just one big line forever?
Mendeleev decided that he would arrange them by weight, but also by family.
This is one of Mendeleev's charts. You can see hydrogen sticking out just as it does today. The families he knew are now arranged in columns. This one has the metals, lithium, sodium, and potassium, that explode in water. Next door, calcium and magnesium, which also react with water. This big block in the middle are metals that are safe to handle, like nickel, iron, zinc, and gold. As we go to the right, the elements become less metallic. These columns are headed by boron, carbon, and nitrogen. In this neighborhood, some elements conduct electricity, some don't, and some can't make up their minds. But next door is a more volatile crowd, headed by oxygen and fluorine. The table gets its shape from the properties of the elements, like relative weight, conductivity, and reactivity. It's true today as it was in Mendeleev's time. Though his chart displayed only the 63 elements known at the time, his understanding of the family properties was so strong he was able to leave gaps in his chart, bold predictions of elements yet to be discovered. And when they were eventually found, they proved completely consistent with his descriptions. Mendeleev lived until 1907, long enough to see 3 gaps filled by the discoveries of scandium, gallium, and germanium. Since his death, dozens of new elements have been discovered, and incredibly, his chart perfectly accommodates all of them, including an entire group that fits neatly onto the end of the table, the noble gases.
Where does that term noble gases come from? Are they nobility? Do they rush to rescue maidens?
No, you're thinking of heroes. They're like nobility in the sense that they don't mix with the riffraff. They don't like to react with any other elements. By and large, it's not possible to form compounds with them.
Well, it's a shame for your collection that they're gases because you've got big blanks here. Oh, ho, ho, ho.
The noble gases, like neon and argon, pose a problem for chemists who prefer their elements to join forces and react with each other. You can run an electric current through them, excite their electrons, and get pretty colors, which is how neon lights work. But the noble gases don't react. They pretty much refuse to combine with other elements.
Being an inert gas, being unwilling to mix with the other elements, react with them, this is a very clear-cut distinction that sets apart this particular column from all the others in the periodic table.
So why are these guys so aloof? As it turns out, protons may determine the identity of an element, but electrons rule its reactivity. And reactivity is a shell game. Here's how the game is played. Imagine that these balls are electrons, and the target is an atom. Electrons don't just pile on around the nucleus. As with skee ball, where you land relative to the center counts.
Oh, come on!
The electrons take up positions in what can be thought of as concentric shells. The first shell maxes out at just 2 electrons. The next holds 8, then it goes up to 18. An atom with 8 electrons in its outer shell makes one happy, satisfied atom. And noble gases come pre-equipped with completely satisfied shells.
And is this the only column like that?
It's the only column where all the shells are completely filled.
But what about the column just before those stable, noble gases? They're called the halogens. They have an outer shell that needs just one more electron to be full, and they'll grab it any way they can. The group includes fluorine and bromine, but the most notorious is chlorine. 17 protons surrounded by 17 electrons, arranged in 3 shells of 2, 8, and 7, one short of being full. It's that extra electron chlorine will get any way it can, sometimes with violent results. That's why chlorine gas was used as a deadly poison in World War I.
Chlorine, I mean, this is nasty stuff. This will take electrons from kittens. You know, it'll go and steal an electron off the water in your lungs and turn it to hydrochloric acid because it really wants an electron.
Yeah, maybe I'll leave that where it was.
Now, if you go the other direction, you end up with the alkali metals.
The alkali metals are the first column. Each of them has full shells plus one extra electron sitting in a new outer shell. They have familiar names like lithium, sodium, and potassium. And they all want to get rid of that single lonely electron any way they can.
So those on that end of the table all have one extra. This column all has one too few. I shudder to ask, what happens if you put those 2 alone in a room?
I happen to have a place where we might be able to do that.
Am I invited?
Please, come to my lair.
Turns out there's more to my friend Theo than mere love of table. He's also got a deep love of chemical reactions and a very remote location where he's free to indulge it.
Okay, they told me you were outstanding in your field, but this is ridiculous.
Yeah, well, you know, the secret to a good mad scientist's lair, no neighbors.
Theo has an infectious attitude toward the most reactive elements.
Nice!
Which reminds me of a snake handler's affection for his most venomous pets.
Oh! Oh, the humanity!
And one of his favorite temperamental friends? Sodium. Symbol Na. 11 protons and 11 electrons, arranged in shells as 2, 8, and 1. Sodium is an alkali metal. Like all the elements in this group, it's desperate to get rid of that extra electron.
You cut it quickly.
I should see some
You should see a silvery surface inside.
Indeed, wow!
It slices like cheese, but it's actually a soft metal. Teo's offered to put on one of his favorite sodium demonstrations. What happens when the pure element dumps its outer electron in a violent altercation with ordinary water? He insists we wait until nightfall, when the reaction will be most spectacular. Kids, do not try this at home.
The whole purpose of this contraption is just to dump it into the bucket of water?
Yeah, it's a sodium dumping machine.
All right, let's give this a try. Here we go. Nice. Oh!
What we're seeing is what happens when sodium's extra electron tears apart water molecules, releasing flammable hydrogen gas, the H in H2O, which explodes when it mixes with air. The next day, Teo takes it up a notch. As if sodium plus water weren't violent enough, now he wants to combine the same deadly sodium with another lethal element, chlorine, one of the halogens. The result, he claims, will be a tasty flavoring for a net full of popcorn?
Isn't chlorine deadly poison?
Absolutely. I mean, chlorine, they used it as a poison gas in World War I.
It'll be perfectly safe when these two deadly ingredients combine.
I didn't say that. I said that after they're combined, the result is perfectly safe. The actual process of combining them is fraught with difficulties.
Okay, and that's why we're dressed up like miners here.
First, a hunk of sodium in a dry metal bowl. Then, a jet of pure chlorine. Surprisingly, no explosion. Somehow, when these two bad boys of the periodic table come together, they calm down. At the atomic level, sodium, an alkali metal, had an electron it didn't want, and chlorine, a halogen, wants desperately to grab an electron. Once the handoff was complete, both atoms wound up with full shells, making them stable, and able to join together to form a crystal compound we can't live without. Sodium chloride, table salt.
Now, I don't exactly see, like, a pile of salt anywhere.
Now, the salt, most of it went up in the smoke. It went in the popcorn.
Tastes like salt. The good stuff. Fresh.
Fresh
Only
salt.
the freshest salt at Teo's farm.
Teo's backyard reactions have given me a crucial insight. How elements come together to form compounds is all about electrons. Which brings me to one of the most notorious electron hounds on the table. Oxygen, symbol O. 8 protons, 8 electrons. It wants 8 electrons to complete its outer shell, but it has only 6. So it's always on the prowl for 2 more. And it's more determined than almost any other element on the table. To get a first-hand look at oxygen's lust for electrons, I've traveled to the Energetic Materials Research and Testing Center at New Mexico Tech, where the business of violent reactions is booming.
What he has here in the rear is 4 pounds of C4.
4 pounds?
It's a deadly serious business for researchers who study improvised explosive devices, IEDs.
By adding the 5/16 nuts, now we have something that's going to get propelled out of here at a few thousand feet per second.
They have a wide variety of explosives on hand. On a typical day, they might blow up a suicide vest, a few pipe bombs, and a briefcase bomb. Tim Collister's job is to train law enforcement and fire professionals how to deal with these dangerous weapons.
Man.
But today, I'm his only student. We're going to set off one of the most powerful off-the-shelf explosives there is. In the trunk of his car, 300 pounds of ANFO. Unassuming white pellets that contain enough oxygen, as well as nitrogen and hydrogen, to turn this car into a scrap heap. Basically, it's a fertilizer bomb.
This is not something I'm going to soon forget.
No, you're not.
3, 2, 1.
Hundreds of pounds of solid explosive transformed in a millionth of a second into an infernal ball of superheated gas, expanding at more than 10 times the speed of sound. A devastating chemical reaction, yet many times smaller than the most notorious ANFO bomb ever detonated. In 1995, over 4,000 pounds of ANFO loaded into a rented truck destroyed the federal building in Oklahoma City, killing and injuring hundreds of people. It's incredibly destructive stuff. How does it work?
I don't know about you, but I am not seeing much car over there.
That's because there's not much car left, David.
To find out, I turned to the lab's chief research chemist, Krista Hockensmith.
The tires are still there.
She's an expert in the chemistry of explosives.
Wow. Whew, doesn't smell so good, does it?
No. You know, we thought maybe the engine would become a projectile to come hurtling out. The engine did not leave, but the entire car did. This whole front half of the car used to be parked over there.
With her help,
look at this.
I'm going to conduct a forensic investigation of the blast site.
Cadillac.
But there's not much left.
What kind of evidence can you derive from this? I mean, the car is totally decimated.
No, we can do good work on finding out what caused this explosion with the magic swabs.
We know what was in the bomb.
Getting the hang of this now.
Yeah, you are. You're getting good.
But in an actual criminal investigation, this work is vital.
We're not picking up only filth. What we're picking up is what the bomb was made with.
You think there's going to be traces even on this fragment?
Not if you stick your fingers on it, no. But otherwise, yes. What you're going to find is when we take these back to the lab that we'll be able to tell what elements were present in the bomb.
So much energy released so quickly. Did oxygen have a role?
Still runs.
So, David, what did you think of that car bomb?
Wicked cool.
Yes.
You have the luckiest job in the world.
You got the swab?
Here's your swab.
Okay.
Krista instructs me to dip the pad into purified water
like that,
to dissolve any chemical traces recovered from the debris.
Covered with paper pulp?
No, covered with nasty.
There you are. You're like this. Shall I suck it up?
Please. That's plenty.
Okay.
Stick it right back into the ion chromatograph.
And you'll just feel a little pinch.
The iron chromatograph looks for positively or negatively charged molecules called ions in the residue.
That looks good.
Fragments of the original chemical explosive.
Well, there appears to be a spike right here at number 3. What use is this analysis? Can you tell the State Department where the bomb came from, or?
I can.
Really? And have you? I mean, do they bring you?
I can't talk about that.
Oh, you can just say yes or no. You can wink.
No, I can.
Different elements show up as spikes in different locations on the graph. Krista tells me this spike indicates that oxygen is at work here, contained in molecules called nitrates. Nitrates consist of 3 oxygen atoms bound to a central nitrogen atom. To set off the bomb, an initial spark of heat breaks those bonds. Once set free, oxygen rushes away from the nitrogen to combine with the elements it prefers, carbon, hydrogen, and even other oxygen atoms, leaving the nitrogen to pair up with each other. Every time atoms form a new bond, the reaction releases energy, and that's what powers the explosion. But in fact, we see similar oxygen reactions every day, like ordinary fire. The heat of this flame is generated when carbon atoms in the wick bond with oxygen in the air. Or rust, a very slow reaction when iron and oxygen combine. Oxygen makes engines rev, rockets roar. And in exactly the same way, oxygen reacts with the food we eat, releasing energy like countless tiny fires burning in our cells, keeping us alive. All of these combustion reactions are essentially the same. The only difference is speed. So how do you speed up a fire to create an explosion? You regulate the amount of oxygen and how closely it's packed together with other elements. As a final demonstration, Krista wants to show me how chemists have learned to control the speed of combustion. She's arranged the use of a high-speed camera to record several different types of explosives. We take cover.
Bunker.
Bunker! The first demonstration will be ordinary gunpowder. So pure gunpowder as our first test here, right?
Yes, this is smokeless powder.
Whoa! Nicely done! It was quick, but it wasn't blisteringly quick. The gunpowder contains its own oxygen, but it's in a mixture of powdered chemicals held far away from the carbon it needs to bond with. But when they finally find their partners, the new bonds they form release lots of energy. Gunpowder is a relatively slow explosive. That's why it's used in guns. It creates enough force to fire a projectile, but not enough to damage the barrel. So you're saying there must be explosives that don't take that long?
We're going to get faster and faster.
Next is an emulsion gel explosive. Its main ingredient is ammonium nitrate, the same stuff that blew up the car. A lot more oxygen and a lot of nitrogen packed very closely together in a liquid.
3, 2, 1.
Oh, jeez. Man, I could feel that puppy through here. This is a high explosive. It generates a shockwave that moves faster than the speed of sound. In this explosive, oxygen, hydrogen, and nitrogen are so close together, they lose no time finding new partners and making new bonds that release energy. The final demonstration is 1 pound of C4, a military-grade high explosive, which burns fast enough to cut steel.
Oh, jeez.
There was nothing to see. It was there and it was gone. C4 assembles oxygen, nitrogen, hydrogen, and carbon in high concentration, close together all on a big molecule. So the speed of the reaction is blisteringly fast. And that gives me an idea. Maybe C4 can help me exorcise a personal demon. What can I say? I have issues. Quite frankly, Chris, I've been looking forward to this one the most.
I am with you 100%.
Clown?
Let's do it to the clown.
Let's do it to the clown!
3, 2, 1.
Okay, well, the world is -1 clown, and I am out of therapy. The oxygen that powers all those explosions makes up 21% of our atmosphere. It's the most abundant element in the Earth's crust. It's also a big part of us. Which makes me wonder, what other elements make life possible? What, for example, is in me? What's in a David? Amazingly, I'm mostly made of just 6 elements. Non-metals, mainly from a small neighborhood on the periodic table. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Or, as some prefer to call them, schnapps. These are the elements that form the basis of all living things. From the most primitive bacteria to the largest creatures on Earth. It seems incredible that so much diversity could spring from such a tiny list. But what I don't get is, why these 6? Why schnapps? Professor?
Yeah?
Sorry, I'm a little late for class. Chemistry professor Christine Thomas at Brandeis University has agreed to help me understand what makes me tick. I was told that you can help me understand CHNOPS, schnapps, the elements of life.
Schnapps, I see.
Better than that, she's going to show me the actual elements in the actual quantities that are in me. but I don't get how.
I've prepared for you a schnapping list.
A schnapping list. You'll have to show me this. Where do you go to find the elements that make up a 185-pound man? Isn't it a little weird that we're shopping for the elements of life at a hardware store?
Does seem a little strange at first.
But in fact, they're all here in these aisles, starting with C, carbon.
All right, charcoal, right over here.
Charcoal? I don't think of the human body being made of charcoal.
Oh, well, it's made of carbon, and, just trust me, you'll see.
Hydrogen?
Yep, that's next. We're gonna get it right here in water. In fact, we're gonna get both hydrogen and oxygen all in one place. All right, so next on the list is nitrogen.
This is fertilizer.
It is, and fertilizer, as it turns out, has a lot of nitrogen in it, just like you.
I've been told I'm full of...
Next is phosphorus.
I'm not seeing phosphorus.
There's, in fact, phosphorus in these matches. You're probably gonna need, well, probably all of the matches that they have here. There you go. Oh, that ought to do.
Hi there. How are you? Just a couple things. We're having a couple people over for a grill. $168? All the vital elements in this magnificent body, $168?
Yep, that's it.
So you're telling me that our hardware store haul here actually is a representative of the schnapps elements in all life and roughly in the right proportions?
Christine tells me we did pretty well, but we didn't quite nail it. We're still missing most of the phosphorus we need. Luckily, she knows where to get some, thanks to a discovery by a 17th century alchemist named Hennig Brandt. Brandt was looking for precious gold, and he thought he might find it in a bodily fluid that looks golden indeed.
All right, so we got to get some urine, and we can get phosphorus from it.
Actually, you're going to provide a urine sample for us to study.
Okay, anything for science. Turns out the amount of phosphorus in my sample is microscopic. We're going to need a lot more. So, back to the stable. Centuries ago, Hennig Brandt had to collect gallons of urine for his experiment.
Wow, I didn't think you had it in you. Very impressive.
Very funny. It was a lot of work, frankly.
The next step requires a concentrated sludge, which is urine minus most of the water. Brandt's early process caused the phosphorus to rise as a vapor, which Christine directs safely into water because phosphorus is dangerously reactive in the air. While that's underway, it's time to get the lowdown on the stuff we bought. Starting with carbon. 6 protons, 6 electrons in 2 shells. Its pure forms include graphite, diamond, buckyballs, nanotubes, and graphene.
You mean charcoal?
Well, we bought charcoal to represent carbon because it's made up of mostly carbon. Carbon in its elemental form looks like this graphite here, like you'd find on the inside of a pencil. What charcoal is mostly is just leftover, say, burnt wood. When wood burns, what's eventually left over looks an awful lot like this charcoal, or this carbon.
And the stuff in charcoal happens to be the foundation of all life on Earth. and for good reason.
Carbon is the backbone of living things because since it can bond to itself, it can form these long chains of molecules.
Long chains can form because every carbon atom needs 4 electrons to fill its outer shell, which means it's eager to bond with up to 4 others, even carbon atoms. Virtually all long molecules in the body are built around carbon.
Your body's about 18% carbon, which for you would be 33.3 pounds, which is equivalent to about 2.5 bags of charcoal here.
All right, so next we have nitrogen.
We do.
For this you bought fertilizer.
Right, so fertilizer is made up of a very large percentage of nitrogen because plants actually use nitrogen as food.
So how much actual nitrogen is in a guy like me?
So your body's about 3% nitrogen, so in your case, that's 5.6 pounds.
Okay, hydrogen and oxygen. You have these tiles stacked side by side. Hydrogen and oxygen, H2O, in water, a twofer.
Hydrogen and oxygen can actually be separated from water using a little bit of electricity.
Electric current breaks up the water molecule. The result is these tiny bubbles of hydrogen gas. Turns out they're really quite volatile. Oh! What the electric current accomplished by separating water into hydrogen and oxygen, a simple flame put back together again.
Now, notice what you see on here. It's a little cloudy, right?
That little foggy spot on the test tube is brand new water, made just now by burning hydrogen and oxygen. Hydrogen is the lightest atom in the universe. So even though there are more hydrogen atoms in me than any other kind, it adds up to only about 18 pounds. Next, oxygen, also in water. Of course, I know how much fire likes pure oxygen.
So why don't you go ahead and light this twig here on fire. When you see it starting to glow, go ahead and blow it out.
Whoa! You have created fire! Okay, so how much oxygen is in me?
In a person's body, there's 65% oxygen. Actually, in your body would equate to 120 pounds.
That makes it sound like I'm a Macy's Thanksgiving balloon or something.
Right.
But as Christine has already demonstrated, it's not in me as a gas. It's in all that water. And this brings us to P. I mean, of course, P as in phosphorus. Hot phosphorus vapor, when cooled in water, turns into a solid.
Yes, we've actually condensed it here as a nice chunky white solid. Phosphorus is actually involved in something really important called ATP, which is the molecule that all cells use for energy.
Altogether, phosphorus makes up about 1% of my 6'2" body. Phosphorus was the first element isolated from a living creature, and it must have surprised Brandt. Exposed to air, it glows, creating what he described as cold fire. This chemical glow is what we mean today by phosphorescence. And when burned in oxygen, it generates a spectacular pulsing display called a phosphorus sun. No wonder it's used to provide energy in our bodies. And to think where it came from. There's just one thing left on our schnapping list: sulfur. I don't get it. What does a tire have to do with sulfur?
So there's a very small fraction of sulfur in this tire, and as it turns out, there's the same amount of sulfur in this one tire as there is in a 185-pound David.
Which is about how much?
Which is about half a pound.
Altogether, just those 6 schnapps elements make up 97% of the weight of my body. But what about the other 3%? And so whatever is left over in those different beings must be what differentiates one from the next.
Right, there's what's called the trace elements, and the person that would be better to talk to about those might be someone that's interested in maybe sports medicine or professional athletes.
Let's see, who could tell us about sports, athletes, and elements? Who could tell us? Hey, are you Lindsay?
Yeah, I'm Lindsay.
David.
Nice to meet you, David. Welcome to the Gatorade Sports Science Institute.
Gatorade Sports Science Institute. I know you guys are involved with elements in the body and athlete performance. I actually am very concerned with these things too. In fact, every morning I take supplements. I use organic elements. I make my own. Calcium, very important. So sometimes I'll mix it up, get a little chalk. Might look like soap to you, but it's a fine source of potassium, iron, zinc, magnesium,
I like to think of this as an excellent source of sodium. And this is it, every morning. You know, it doesn't taste fantastic, but wow, is it good for me. Am I going about this the right way?
Actually, David, there's a better way to get your elements, such as calcium, iron, magnesium, in your daily food intake.
But this is organic free range.
I'm curious to know how my body uses those trace elements. But first, a battery of tests to determine what kind of shape I'm in. Once I've been poked,
Go ahead and take all of your clothes off.
Okay.
weighed,
David, I said all your clothes.
measured, and scanned, and by the way, in the real world, this costs some serious money, she puts me on a treadmill to measure my oxygen use, which could be impaired if I have an iron deficiency.
Okay, and start. We'll get to a nice comfy walking pace. 15 seconds, we're gonna increase the speed. Okay, David, what's your rating of perceived exertion? Keep pushing. Okay, David, how do you feel at this stage? 15? Where are you at now? He's at an 18, okay. 10 more seconds, as hard as you can. You can do it. Okay, you got any more left? Okay, okay, go ahead and go ahead and grab onto the railing. That's good, that's good.
Next, a sweat test.
Okay.
All the way down, good. Lock out at the top.
This is how OSHA violations happen.
Kick it and reach it.
You know, if you play this video in opposite way, it looks like I'm really running. Thank you, sir. It's been a pleasure. Go train somebody else.
We're just getting warmed up.
Unfortunately, he wasn't joking. Now they're ready to start the actual test. These patches will collect my sweat, which in turn will tell Lindsay how much of the trace elements I'm losing from my body.
I feel like an old tire.
Here we go, ready, go.
Shouldn't you have a mower attachment at least?
Come on, drive it, let's go. Come on, stay lower. Use your butt, use your glutes. Finish it, finish it. All the way down, all the way up.
Like that?
There you go. A little higher, let's go. I'm gonna start calling you names in a minute, let's go.
Oh my God.
Keep going, that was 2. 3rd grade girls can get 10. Let's go, keep going. Excellent job. Yeah, great job.
Sweaty pads.
That's right.
Come and get them. So the purpose of all this was to measure what electrolytes and salts and stuff are leaking out of my sweat, right? And why exactly do we care? Why do you care in the athletes you train here?
What we want to prevent is athletes cramping, affecting their performance, not only in practices, but also in games.
So you could be properly hydrated and still get cramps?
Correct.
Well, thanks for the education and thanks for the workout, Coach.
You bet, anytime, Dave.
And now for the results. My bone density test, normal. Plenty of calcium in me.
So you have nice, strong bones.
So that means that my morning ritual of consuming calcium seems to be working.
It is working. However, I would suggest dairy products to get your calcium instead of seashells.
The treadmill, not so good.
For your age and compared to other males, you're in about the 30th percentile.
That's low.
It's low. It's below average.
This could mean one of 2 things. Either I might have an iron deficiency, so my blood isn't carrying enough oxygen, or I'm really out of shape. And my blood test showed I'm not iron deficient. So, well, what about the other elements? What do they do?
Zinc?
Zinc is important for energy metabolism.
Potassium?
Potassium is an important part of nervous system function.
Magnesium?
Energy metabolism.
Okay.
And finally,
what about sodium?
So sodium is important for a nervous system function. That's why we did that test on you today.
Luckily, my test results were normal. I may have been sweating a lot out on that field, but I sweat like a champ. In total, the human body uses more than 25 elements in ways and quantities that are unique to us. Not every living thing does it the same way. Take oxygen. We love the stuff, can't live without it. But it wasn't always this way. When life began, conditions were very different on Earth. To begin with, there was no oxygen in the air. To learn what put the O in our atmosphere, I've traveled to Yellowstone National Park. David Ward has spent his professional life studying the Earth's most ancient organisms.
So Dave, you're a microbe expert, I hear.
I am. I am a microbial biologist. I study microorganisms, and I'm particularly interested in how they evolved.
Well, when you say the earliest ones, how old are we talking about?
We're talking 3-4 billion years ago.
Yellowstone sits atop the largest volcanic system in North America. That unusual geology creates hot, poisonous pools that Ward sees as a window into the past.
You've installed a hot tub here.
The park permits Ward to collect samples from these protected environments.
So this is you. This is your office, huh?
Yeah. Now, you are not actually allowed to be inside the rocks. You have to have special sampling permit. You stay here, and I'll go on across.
Let me know if you need a bottle of water or something. What is that gizmo you have there?
This is a thermistor. It takes temperature.
Oh, we call that a thermometer.
You know, scientists have to have fancy words for things.
Scientists think that in order to get the energy they needed to live, some of the earliest forms of life required extremely hot water, mixed with elements like hydrogen, sulfur, and iron. But as the planet cooled, another ancient microorganism evolved and changed everything. They are called cyanobacteria, but we know them as blue-green algae. They found a way to get their energy from light and water, releasing oxygen as a byproduct, just like modern plants do. The evolution of cyanobacteria set the stage for all the plant and animal life that followed.
And in fact, you can see that clearly here. You can see this orange to brown transition.
Yeah.
And you know, this is one set of species, and then there's another, and then finally this third.
Dave Ward offers to introduce me to one of my oldest living relatives, with the help of an ordinary drinking straw.
And we'll take a sample here, and this is the real high-tech part. I use my high-tech soda straw. Is take aim and push the straw in and just immerse it into the liquid nitrogen.
Wow, snap frozen for freshness, huh?
Yep.
The different colors are actually different species of microorganism. Back at his lab, Ward prepares the sample.
There we go.
Here in the layers, we can see different species living together, separated by hundreds of millions of years of evolution. The thin greenish layer on the top is cyanobacteria, situated at the best spot to find light, water, and carbon dioxide for growth. And in the history of life, it's the cyanobacteria and us that truly came out on top.
Take a peek here, Dave.
As they spread out of the volcanic pools and colonized the planet,
Oh my gosh.
these tiny organisms pumped out more and more oxygen. For a few 100 million years, oxygen simply reacted with the metals in the Earth's crust, and the planet slowly rusted. But eventually, the oxygen began to build up in the atmosphere, and those little bugs are still hard at work today.
These little critters that are making half of the oxygen that all of the things requiring oxygen breathe today. So they're still at work making all of this oxygen.
These microbes changed the face of an entire planet. But where did the elements of life and all the other elements come from in the first place? Let's start at the very beginning with hydrogen. 1 proton and 1 electron. Around 90% of all the atoms in the universe are hydrogen, and they were all made by the Big Bang more than 13 billion years ago. But where did things go from there? The answer is in the stars. Like our own sun, a seething cauldron of hot gas, constantly turning hydrogen atoms into element number 2, helium. It's a process called fusion. And now, scientists at the National Ignition Facility in California are actually trying to recreate that solar process here on Earth. If they can make it practical, and that's a big if, they could unlock a new source of limitless, clean energy.
So the world is going to be using more energy.
Ed Moses is a physicist who's leading the effort. And his raw material is hydrogen, the smallest and the oldest element in the universe.
Around 30 seconds after the Big Bang, all of that hydrogen appeared.
From the Big Bang?
From the Big Bang. It sort of has an infinite life. So when we drink a glass of water, are sampling the Big Bang.
Fusion forces two hydrogen atoms to merge into a single helium atom. Pound for pound, it's the most energetic reaction in the cosmos. And that's what his facility would like to reproduce.
We crash them together, and what happens is we turn mass into energy, just like Einstein told us.
To do this, Ed's team focuses 192 of the world's most powerful laser beams onto a BB-sized capsule containing hydrogen atoms. This fuses them into helium atoms and releases a 100 million degree pulse of energy. The goal is to create a sustained fusion reaction, but right now it lasts only a billionth of a second. Stars create helium throughout their long lives, but in their old age, they run low on hydrogen and begin to fuse helium, creating larger and larger elements.
And you'll start walking up the periodic table, making more and more elements. First you made helium, then you'll make lithium and beryllium and boron. And you can do this all the way up to iron.
By the time it's fusing iron, a star is in its death throes. It begins to collapse, and if it's massive enough, that collapse leads to a powerful explosion called a supernova. In that intense flash, the supernova creates elements heavier than iron, launching them all into the cosmos, creating the raw materials of planets and of life. And now we're using those raw materials to shape our civilization with elements like silicon, 14 protons, 14 electrons, the second most abundant element in the Earth's rocky crust. A member of one of the smallest neighborhoods on the table, the semiconductors. When most people think of silicon, they think of computer chips and the information age, but its most familiar form is actually in this. For more than 5,000 years, silicon glass has brought light and beauty to our lives. Today, scientists are re-engineering this ancient material, atom by atom, here at Corning in upstate New York.
You know, David, this place looks and sounds like a blacksmith shop, but actually it's a scientific laboratory.
They're fiddling around with various combinations of elements,
That's
seeing
right.
what kind of glass comes out.
They tell me it all starts with ordinary sand, which is made of a combination of silicon and oxygen. But sand is opaque, isn't it? It turns out it's much more glass-like than I thought.
Under magnification, sand looks like little tiny glass jewels that are essentially transparent.
So the light's coming from underneath these grains of sand and
That's
shining
right.
through
Yep.
them?
And, you know, it shows that it's transparent.
That is so weird.
Melting sand and then allowing it to cool begins to turn it into glass.
Feels like thick, heavy vinyl.
Glass is surprisingly strong. It can withstand a lot of crushing force, but it's also very brittle. Is there any way to get around that weakness?
What the scientists do is they can tailor the glass by adding other things other than the sand to engineer the properties that they want to into the glass.
Should I worry that my gloves are on fire?
Changing the 5,000-year-old recipe for glass has led to a new form they call Gorilla Glass. And you can probably guess why they named it that.
Something that we call a drop test, where the glass is in a frame, like we have a piece of Gorilla Glass in this, and the ball is dropped from a height of 1 meter.
How thick is this piece of glass?
This is 0.7 millimeters.
Not even a millimeter?
Not even a millimeter thick.
We're gonna drop 4 pounds on that?
That's right. David, this is our hail gun. It shoots a ball of ice at 60 to 70 miles an hour.
Ready, aim, hail!
So this is a sample of our special glass.
This is plastic, dude. I can make a paper airplane out of this.
Yeah.
It didn't break. Oh my gosh, it's gonna fold it in half. There's a lot of bend to it. Ready, aim, fire!
The secret behind these weirdly durable forms of glass is engineering on the atomic scale.
Sweet! Clearly it worked. The 70-mile-an-hour golf ball-sized hail did absolutely nothing to it.
The glassmakers have learned how to precisely place minute amounts of metal atoms, like sodium, potassium, and aluminum, among the silicon atoms. The result is hard, yet flexible, and scratch resistant.
No!
But is it really glass?
So you maintain that this is not, in fact, plastic, that this is actually glass.
But yet very strong. Within reason. There's no such thing as an unbreakable glass. It is a glass. It is a glass. So there are limits.
These days, we need strong glass for lenses, fiber optics, and screens of all sizes.
Hey, I'm on TV!
But silicon's work is not yet done. Because underneath the glass, there's a lot more silicon in the guts of all those electronics. Silicon is the standard bearer of the semiconductors, materials that change from free-flowing conductors to non-flowing insulators when we simply zap them with an electric current. Switches made out of semiconductors made computers possible. But lately, when it comes to high tech, there's a new family on the block: the rare earths. 15 elements located near the bottom of the table. And in my job as a technology writer, there's one rare earth that interests me more than any other: neodymium. It's the key ingredient in the world's strongest magnets. They're critical to computers, cell phones, hybrid cars, wind turbines, even tiny earbuds. Without neodymium, we'd be sunk. So that raises a question. If they're in everything, how come they're called rare earths? The best place to find out is at the source. John Burba is the Chief Technology Officer at Molycorp. He's overseeing a billion-dollar operation to bring this 50-year-old mine into the 21st century.
So how many rare earth mines like this are there in the United States?
One.
This is it?
This is it.
One mine in the United States. And John tells me it's not even fully operational yet. So,
where do rare earth minerals come from in the world?
The majority of it comes from China.
What kind of majority?
Like 98%.
98% of these minerals come from China?
Yes.
Then he breaks the news that the Chinese government has been limiting the export of these strategically important elements. Seems like the fate of the free world could be riding on these rocks. I'd better get some of my own, while the getting is good.
But look for stuff like this. We'll find out how good a geologist you are.
This reddish stuff?
Yeah.
This is a hunk of what?
Barite, barium sulfate. It's got some monazite in it. They're naturally occurring crystals that contain the elements.
So can I get a few more of these?
Yeah, just look for stuff that's similar.
You know what, John? I like these two a lot. I can't decide. It's an either-or situation. So how can I find out which elements are in this hunk?
Molycorp's facility is still under construction. So to find out what's in my rocks, he suggests I take them to the world's premier rare earth research lab in Ames, Iowa.
Be there soon.
I'm dying to know what I've got my hands on. A pinch of praseodymium, perhaps? A whole pound of holmium? A thimbleful of thulium? Or, dare I hope, magnet-making neodymium? If anyone can extract all the precious neodymium from my rocks, it's these guys.
David, I've been expecting you. Good
David,
to see you.
how are
yes,
you?
sir. Yes, sir. I see you brought the ore with you.
I brought this all the way from California.
All the way. All right.
I cured it by hand because, you know, it's rare earth.
It's rare earth.
Ore, and I didn't want anything to have. I didn't check it. I didn't put it in the overhead.
Okay.
I think I've got some beautiful samples.
Oh, yeah.
There's this mine in California, the largest one in the United States. Look at the size of this mother.
Yeah.
I think this one's my favorite.
Oh, yeah.
Thought if we brought it here to Ames Lab, I thought you could do a little chemical analysis on it.
We certainly can. Well,
So,
let's see.
yeah,
We'll
watch out
take your
with the-
favorite one and
watch out with the hammer.
see-
What do you-
oh yeah, there we go. That's a good piece right there. That's all we're going to need for the chemical analysis. So the rest of this we'll just throw it right here in the trash.
But that's rare. California.
The truth is, rare earths are not rare. They're just notoriously hard to separate. The problem is, at an atomic level, the rare earth elements all look weirdly alike. Moving from element to element along a row of the periodic table adds a proton to the nucleus and an electron to the outer shell. But in the rare earths, the new electron disappears into an unfilled inner shell. The result? 15 atoms that all have identical outer electron shells, making them virtually indistinguishable chemically. But what about my rocks?
Okay, David, the ore that you brought us, the rocks that look like this, we analyzed those, and this is what we found. We found major components of cerium, lanthanum, and praseodymium.
But no neodymium. Apparently, my rocks are neo-free. But there was some good news. The ore I brought in contained a whopping 20% rare earth oxide. Molycorp may soon be able to take a big bite out of China's near monopoly. Before I head out, though, there's one more lab I'm determined to visit.
So, David, would you be interested in seeing a rare earth magnet?
Paul is one of the lab's top magnet guys.
This is a rare earth magnet. This is actually neodymium, iron, and boron. This is, about 150 grams of the world's highest purity neodymium.
Neodymium magnets are a bit of a misnomer. They're really iron magnets with a pinch of neodymium added like a powerful spice to make them stronger, plus a few boron atoms to help hold everything in place.
You grow these? You don't dig these out of the ore somehow?
No. These don't exist in nature. These are things that we have to combine and cook in the same way that huevos rancheros doesn't exist in nature. It has to be put together.
Paul's lab is like a dieter's kitchen, satisfying a hunger for powerful magnetic crystals while reducing the amount of neodymium needed in the recipe. And he's just about to whip up a fresh batch. The main ingredient is ordinary iron. Iron makes magnets.
There you go.
But adding neodymium makes magnets on steroids. Here's how you make a magnet. First, all the solid ingredients are sealed into a quartz tube to be melted together.
David Pogue, scientist.
After some time in the furnace, tiny magnetic crystals have formed in the melted iron.
2,000 degrees. Oh my gosh, it's like threading a needle.
The next step is to separate the solids from the liquid.
Dump it in, slam the lid.
They put the centrifuge on the floor for safety, in case anything goes wrong with the super hot vial.
We turn it off, it lets you open it up, and we can take it out. We have single crystals of the neodymium iron boron separated from the extra liquid, which the centrifuge separated with the 10 to 100 Gs.
The result of all this cooking and spinning? A powerful magnet that uses less neodymium, we hope.
It sounds like you're saying you're trying to use as little of the rare earth as possible.
Absolutely.
Why? Because I thought rare earths aren't really that rare.
The rare earths are not rare, but they're hard to separate, and that's part of the expense.
Even with Paul's help, it looks like rare earths are going to remain in short supply, at least for now. Partly because scientists continue to find surprising new ways to use these strange metals. Like marine biologist and conservationist Patrick Rice. If he has anything to say about it, rare earths may be coming soon to a fish hook near you.
Oh, is this your little kiddie pool where you bring the children to swim?
This is our little tank here where we have a couple little bonnethead sharks and a little nurse shark in here.
All right.
Okay.
Rice was searching for the next great shark repellent when he made an accidental discovery that looks like it'll be good news for both man and fish.
We had sharks in a tank like this, and a pump broke on one of our tanks. And so we were playing with these magnets, and we put the magnet down by the tank to go fix the pump. And when we put the magnet by the tank, the sharks took off.
Somehow, the sharks inside the tank sensed the presence of magnets outside the tank. And when they did, they voted with their fins. Patrick offers to demonstrate the weird repulsive effect. He hands me a case of super strong magnets.
So this is full of actual regular old refrigerator. Oh, yeah, more than refrigerator magnets.
That's right.
Okay.
That's right.
And you're saying that this will somehow repel the sharks. Okay, here comes a little guy.
That's a little nurse shark. It might work for him. Tell me when it gets over.
3, 2, 1. Oh my gosh! It's like you dropped that thing on his head.
Yeah, you saw it, huh?
Yeah. He's like, dum-dum-dum, wow! And he
right.
Like whipped out of there.
Right, exactly.
The shark can't see the magnet, but it obviously feels the effect. And it's not happy.
1, 2, 3, now. Boom, you got him.
Really?
Yeah, you got him.
That's crazy.
Isn't that amazing?
Patrick thought he could somehow use this effect to save sharks from being inadvertently caught by commercial fishermen. But there was, so to speak, a catch.
We put the magnet right above the hook on the line.
Oh, okay.
And what was happening was the hooks were swinging around and getting caught on the magnets.
That would
So
happen.
it wasn't catching any sharks, but it wasn't catching anything else either.
But he wasn't willing to give up. He decided he needed to find the weakest possible magnet that would still affect sharks. The first step was to create a baseline for comparison by exposing sharks to non-magnetic materials. He offers to recreate his experiment.
You know, I don't have insurance for this.
Be careful, it might be slippery.
You're warning me about the slipperiness? Dude, there's 3 sharks in here.
No, but they're nice.
Okay, just want to say for the record that I'm standing in a tank full of sharks.
That's correct.
This is like Jaws 7, the kiddie pool.
Step 1, capture a shark.
Dude, you just caught a shark with your bare hands.
Then, flip the shark upside down, which induces a trance state called tonic immobility. Once the shark is calm, we test its reaction to a piece of ordinary, non-magnetic lead.
Would you like me to just honk her on the head with this?
Cover up her eyes.
So it's not a visual thing.
Using a shield to make sure that the shark can't see the metal, I bring it close.
No reaction.
None at all.
As expected. Next, a non-magnetic piece of samarium, a rare earth element. The expectation was that because it's non-magnetic, there would be no reaction.
Oh man, she
didn't like that at all.
This is like kryptonite for sharks.
Yes, it is.
Wow, that's amazing. It woke her up and drove her crazy.
Yep.
So the idea is you could make what out of this stuff?
Well, the idea is that it's not magnetic, so we could potentially incorporate it to a fishing hook. And then you have something that repels sharks, but doesn't have the magnetic properties, so it won't tangle the gear and stuff like that.
The discovery that non-magnetic rare earths have a repellent effect on sharks was a complete fluke. And it works with other rare earth metals as well. But why? What do sharks have against these particular elements?
We believe it's creating a little electric shock.
A little electric shock?
Yeah,
A shark shock.
A shark shocker.
Patrick demonstrates, using a beaker of seawater, a piece of samarium, a voltmeter, and an actual shark fin.
Bum, 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 bum.
When he submerges the samarium and the shark fin in the seawater, an electric current flows.
Whoa! Oh my gosh.
That's almost a D-sized battery.
You're kidding. Did we just make, in effect, a battery?
Correct.
As a group, the rare earths give up their outer electrons very easily. In the salt water, samarium atoms break free of the metal disk and give up one or more of their outer electrons. The atoms become positively charged and are attracted to the shark fin, which, like many biological materials, has a slight negative charge. The movement of the charged atoms creates an electric current,
Wow, that's some real juice flowing.
just like in a battery.
It is like a battery. It's a complete closed circuit, and the voltmeter's measuring that. That's pretty amazing.
Yeah.
But is the effect actually strong enough to put a shark off its meal?
So we've just done our little test.
There's one final experiment we can run to find out.
What we're gonna do now.
Thank you.
You're welcome.
That was just for the blooper reel. We like to get some material.
As I was saying, there's one final experiment we can run to find out.
What we're gonna do here is a little experiment we've never done before.
You haven't done this before?
Haven't done this before.
You waited until there was a national TV camera rolling?
There's a 9-foot lemon shark in this lagoon, and it's lunchtime. Now for the test.
This side over here.
We're going to suspend 2 identical pieces of tuna. One will hang below a piece of lead. That's our control. The other under a piece of samarium.
You go ahead and put it out there.
Really?
Yep.
Lower her down.
If the test is successful, the shark should avoid the samarium-tainted meal, but not the food near the lead.
Here she comes.
Oh, that's.
See?
Oh, she didn't like it at all.
She didn't like it.
She was aiming right at it, and she went like, "Oh!"
That was an excellent response. Notice the other fish doesn't have any effect on them.
Hey, wait a minute. Now she's going for the lead.
So there's the control.
And she loves the lead one.
No problem on the control, so that's awesome.
Since making this remarkable discovery, Patrick has experimented with designs for shark-repelling fishing hooks, and he's seen some promising results.
The last experiment we did, we put out 46,000 hooks, and we reduced shark bycatch by 27%.
Get your fresh chum hit.
Shark zapping is just the latest entry in the growing list of curious rare earth abilities. But perhaps the real shocker is that these 15 elements were so long misunderstood, their identities masked by their identical outer electron shells. But those aren't the only atoms hiding from view. Scientists now know that most elements come in more than one version. The different versions are called isotopes. Consider carbon, the backbone of life. It has 3 natural isotopes, or versions. Each has 6 protons and 6 electrons. That's what makes them all carbon. The difference between them is the number of neutrons in the nucleus. Neutrons are electrically neutral particles that act as glue to hold atoms together. What we think of as normal carbon is called carbon-12, 6 protons plus 6 neutrons. But about 1% of carbon atoms have an extra neutron, giving them 7. They're called carbon-13. And about 1 in a million have 8 neutrons. That's carbon-14. And that rare version of carbon has proven to be a crucial tool for unlocking the past. Several times a year, scientist Scott Stein travels to the shores of Mono Lake near Yosemite National Park.
This then is Mono Lake.
Mono Lake, yeah, right here at the foot of the Sierra Nevada.
He's studying the long history of droughts in California, trying to determine how frequently they occur and how long they last. Over the millennia, the water level has risen and fallen as the area has cycled between wet periods and dry times.
Oh, so that sandy area should be the level?
During times when the climate was dry, Mono Lake dropped down, exposed the shorelands, and allowed trees and shrubs to grow.
When the dry periods ended and the water level rose, the trees drowned, marking the end of the droughts. Since then, the remains of those trees have been well preserved by the arid climate.
These droughts were long persistent.
To determine how long ago these droughts occurred, Scott is using carbon-14 to date the trees. Unlike the other natural isotopes of carbon, carbon-14 is unstable. Over time, its atoms begin to deteriorate. One of its neutrons turns into a proton and spits out an electron. Now, with 7 protons instead of 6, it's turned into nitrogen. That process is called radioactive decay, and scientists know exactly how long it will take for half of any amount of carbon-14 to decay away. Scientists call that time its half-life. Living things constantly replenish the carbon in their bodies. Animals from food, plants from the atmosphere. But after death, that process stops. The amount of carbon-12 stays the same, but the carbon-14 decays away at a constant rate, making carbon-14 a ticking atomic clock. To know how long ago this ancient tree died, we just need to count the carbon atoms in a small sample. Piece of cake, if you're this guy.
No, these are fragments of the tree stumps at Mono Lake, and I understand that you are the master of carbon dating.
Physicist Tom Brown works in the carbon dating program at Lawrence Livermore National Laboratory.
In fact, if I'm not mistaken, carbon dating actually pre-existed before internet dating.
Very much.
Carbon-14 can be used to date samples up to 40,000 years old. It's been used to find the ages of many Egyptian mummies and other ancient artifacts.
So how does wood fare with carbon dating?
Intact wood is very good material to date. It retains the carbon from when that material died, and we're able to extract it, purify it, and get a really good material for dating.
Tom needs only a small amount of wood. Even this tiny sample is overkill. A lab technician cleans it and reduces it to a fine powder.
Oh man, this huge thing? This is your Carbon Dater-Matic 3000?
The actual counting of the atoms takes place here in the Carbon Dating Accelerator.
I see you bought the camping version.
So we have our 1 milligram of carbon from the wood chip sample basically in that hole.
In that tiny little hole?
That's where the 1 milligram of carbon is from that sample.
Not a lot of wood chips.
And we put about 64 of these holders in one of these wheels.
The accelerator applies a powerful electric charge to the atoms, basically lightning, giving them the speed and energy they need to hit a detector with enough force to be counted.
The ratio of the carbon-14 ions to the amount of carbon-12 in the sample tells us how old the sample is.
The fewer the carbon-14s, the older it is?
Yes.
With his accelerator, Tom calculates that our tree died about 150 years ago. That must have been when California's last drought ended, a key piece of information for understanding the region's climate cycles. Carbon-14 has helped open up deep insights into the past, but it's just one of hundreds of radioactive isotopes, that is, elements that decay. In fact, at the bottom of the periodic table, beginning with number 84, polonium, all of the elements and their isotopes are radioactive, including the element that stands for both the promise and the peril of radioactivity, uranium. 92 protons, 92 electrons, and 146 neutrons. Before the nuclear age, uranium was thought to be the end of the periodic table. But in the last 70 years, scientists have left nature behind and created 26 new elements. The age of man-made atoms began in the first half of the 20th century, when researchers began bombarding elements with neutrons. Sometimes the neutron is simply absorbed, creating a new isotope. But sometimes the nucleus can't take the punishment. It becomes unstable and splits into two smaller atoms in a powerful reaction called fission that releases large amounts of energy. To learn more, I've come to the Nuclear Museum in Albuquerque, New Mexico.
Yeah, this is a mad science project.
Where atomic scientist Matt Dennis has offered to demonstrate how a nuclear reactor works.
You guys make a lot of jokes about gone fission.
I actually have an atomic shirt that says something to that effect.
I knew that!
Yes.
I knew that! Okay, now to the naked eye, this looks exactly like a nuclear reactor.
The similarities are the mousetraps are uranium atoms, and the white ping pong balls are neutrons, which you use one to start a chain reaction.
In a reactor, one neutron splits a uranium atom, which releases energy and 2 or 3 more neutrons, which in turn split more atoms, releasing more neutrons, and so on, causing a chain reaction.
So you get more and more neutrons, and thus the chain reaction keeps going.
All right, ladies and jelly spoons, here goes the orange ping pong ball. This evening's role, you'll be portraying the neutron. All right, I just drop it in here.
You just drop it in right there, and we'll start the chain reaction.
Incoming neutron! I'm sorry, Matt. The camera wasn't rolling. Can you set that up again?
From a single neutron, an escalating response. Our mousetrap reactor doesn't have many atoms, so the reaction dies quickly. But pack enough fissionable uranium atoms closely enough together, and the whole thing can get out of hand pretty fast. And sometimes that's the point. This museum has the world's largest public collection of artifacts that chronicle the dark side of nuclear energy.
And so that's a Trident C3 up there.
It's huge. You guys are just surrounded by bombs. I feel like a kid in a death store.
In 1945, the U.S. developed 2 atomic weapons. Both were used against Japan. The first was fueled by an isotope called uranium-235. That bomb was called Little Boy.
This is the Little Boy bomb. This is the very first.
I guess I shouldn't bump it then, huh?
Well, it's a concurrent copy. This is just like it, and inside this big case was a gun barrel and high explosives on the ends to push the 2 pieces of enriched uranium together at supersonic speed.
The military made only one uranium bomb because separating rare U-235 from the more common U-238, which doesn't work in fission reactions, is a very difficult process. So for the second bomb, called Fat Man, they used an entirely different element, plutonium. 94 protons, 94 electrons, and 150 neutrons. plutonium was the first man-made element. It was identified in 1940 by chemist Glenn Seaborg when he bombarded uranium atoms with protons and neutrons until some of them stuck. Over his long career, Seaborg went on to isolate or create 9 more man-made elements, including americium, which is in minute quantities in the smoke alarms in our homes. He pushed the end of the periodic table all the way to element 106, which is called Seaborgium in his honor.
I started out here at the laboratory using these counters quite frequently.
Ken Moody is a chemist at Lawrence Livermore Lab, but he developed a love of big, fat, juicy atoms as a graduate student in Seaborg's lab in the 1970s. Afterwards, his first job was analyzing radioactive debris produced by underground nuclear weapon tests.
And it was our job to go pick samples and tell the physicists how well his device had worked.
I think I'm smart enough to know that those fragments would probably be radioactive.
Yes.
Would they not be dangerous?
Well, we didn't carry them around in our pockets.
Since the end of the Cold War, Ken's goal has been to expand the periodic table. He's teamed up with a Russian lab, and together they've succeeded in creating 6 new elements in this cyclotron. But there's a hitch. They've only made a few atoms of each, and they're all so unstable, they decay away almost as soon as they come into existence.
With all due respect, none of the 6 elements that you've discovered are actually in the world right now.
That's correct.
So do they count?
Doesn't sound like much, but for a chemist, a 10-second activity actually allows you to do something with it, but it isn't enough that you can put it in a bottle and put it on the mantelpiece and admire it the next day.
Still, Ken has high hopes for the future. He believes that somewhere beyond today's largest man-made elements, scientists will find an island of stability on the periodic table, where some super-large atoms will be both stable and useful, perhaps satisfying the needs of our future civilization. It's amazing to think that something as complex as the physical universe can be put on a single chart. And from about 90 basic elements, man and nature have teamed up to create the incredible variety of stuff in our lives. And the story is far from over. As scientists continue to hunt the secrets of the elements, what new understanding and technologies will follow can only be imagined.